Right now, as you settle into wherever you are lying, you are moving, not gently and not slowly. You are being carried in a vast circle around the center of our galaxy at a speed of roughly 500,000 miles every hour. At that velocity, you could cross the entire breadth of the United States, from one ocean to the other, in under 20 seconds. And yet you feel nothing. No wind, no pressure, no sense of motion at all. That number is almost impossible to truly feel. You are moving faster than any rifle bullet ever fired. You are moving faster than the fastest spacecraft human beings have ever built. Faster than the probes we have flung toward the sun on trajectories of pure fire. You are moving so quickly that in the time it takes you to read a single slow sentence, you have already traveled farther than the distance between most great cities. And still, at that astonishing speed, our sun takes more than 200 million years to complete a single journey around the galaxy. In the entire history of the sun, from its birth inside a collapsing cloud of gas to this very moment, it has made that great loop only about 20 times. But here is the thought that should settle over you tonight, quietly, like a weight you can almost feel against your chest. The galaxy is so large that even if you traveled for an entire human lifetime, even at the speed of the fastest machine we have ever made, you would not cross even 1 part in a million of its width. You would be born, you would live, you would grow old, and you would die, and the galaxy around you would barely register that you had moved at all. So how long would it really take to cross the Milky Way? How long to travel from one edge of this great spiral to the other, from the rim where the stars thin into darkness, across the bright crowded center, and out to the far side? It seems like such a simple question, a distance, a speed, a number of years. But here is what most people get wrong. The question does not have one answer, it has several. And each one is stranger than the last, because the true answer depends on something you would never expect. It depends on whose clock you are reading. Tonight we are going to take that journey together, slowly and completely. We are going to begin with how human beings first measured the size of the thing we live inside, a discovery so recent that your great-grandparents were alive before we knew the truth. We are going to discover why light itself, the fastest thing in all the universe, is still hopelessly, heartbreakingly slow against these distances. We are going to follow our fastest machines outward until they fail us entirely. And then we are going to find the strange loophole hidden inside the deepest laws of physics. The one that means a single traveler could, in principle, cross the whole galaxy within one human life, while 100,000 years quietly pass for everyone left behind. If you enjoy slow, calm journeys through the deepest places of our universe, the kind of journey you can simply drift away into, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow, and it lets me keep making these long, quiet, deep dives for you. So make yourself warm and comfortable. Let your shoulders fall away from your ears. Let your breathing slow, and let me carry you, gently and patiently, across the largest thing you will ever be a part of. Let's begin. To understand how long it would take to cross the Milky Way, you first have to understand how unimaginably large the Milky Way truly is. And to understand that, you have to know how recently we learned it. For almost the entire span of human existence, nobody knew. Nobody could have known. The galaxy was not a place. It was not a structure. It was simply a smear of pale light strung across the darkest skies, a faint silver river of brightness that ancient people explained with stories. Because stories were all they had. The Greeks looked up at that band of light and called it the Milky Circle, and they told a tale that the goddess Hera had spilled her milk across the heavens while nursing a child. The word galaxy itself comes from their word for milk. Other peoples across the world saw other things in that same pale ribbon. Some saw a road for the souls of the dead to walk. Some saw a river. Some saw a great seam stitched across the dome of the sky. For thousands upon thousands of years, that band of light was simply there, beautiful and silent and entirely without explanation. And not a single person who gazed at it suspected that they were looking edge-on into a structure so enormous that light itself would need 100,000 years to travel across it. The first crack in that long ignorance came in the year 1610. In the city of Padua, in what is now the north of Italy, a man named Galileo Galilei lifted a newly improved telescope toward that pale band of light and saw something no human eye had ever seen. The Milky River was not a cloud. It was not a vapor or a mist. It was made of stars, countless individual points of light, so many and so faint and so tightly crowded together that the unaided human eye simply blurred them all into a single soft glow. Not a substance then, but a multitude. Not one thing, but uncountable things, packed so densely that they melted into one. It was the first hint, the very first, that the heavens held far more than anyone had imagined, and that we were embedded in something we did not understand. But knowing the band was made of stars is a very different thing from knowing its shape, or its size, or our place within it. Those questions would take another 3 centuries to answer. The next great step came nearly 200 years after Galileo. Around the year 1785, a German-born astronomer working in England, William Herschel, set out to map the galaxy by brute patience. He pointed his telescope in direction after direction across the sky and simply counted the stars he could see in each one, a painstaking method he called star gauging. He reasoned that if he saw more stars looking one way and fewer looking another, the shape of the whole could be inferred from the count. After thousands of careful tallies, he concluded that the galaxy was a flattened disk, a shape something like a grindstone, broad and thin, with the sun sitting comfortably near the middle of it. He was right about the shape. He was wrong, profoundly and understandably wrong, about our place inside it. The reason was simple, and it would haunt astronomy for over a century. Herschel had no way of knowing how much dust floated between the stars, dimming and hiding the distant ones. So the galaxy looked roughly the same in every direction, not because we sit at the center, but because the dust prevented us from seeing far enough in any direction to notice we were off to one side. We seemed central. We were not central. We only seemed that way because our view was equally blocked in all directions, like standing in a fog and believing yourself to be at the exact heart of the world, simply because the fog ends at the same distance no matter where you turn. This same beautiful mistake was made again, with more precision, in the early years of the 20th century. A Dutch astronomer named Jacobus Kapteyn spent years gathering star counts and motions into a single grand statistical model of the galaxy. His picture, sometimes called the Kapteyn universe, was more careful and more mathematical than anything before it, and it was still wrong in the very same way. It still placed the sun near the center, and it still made the galaxy far too small, only a few tens of thousands of light years across. The fog of dust had fooled the finest minds of the age twice over. Here is the problem that lay beneath all of this, the single problem that the entire history of measuring the galaxy comes down to. You cannot simply look at a star and know how far away it is. A faint pinprick of light in the sky might be a dim and modest ember sitting relatively close to us, or it might be a colossal blazing beacon almost unthinkably far away. The two look identical. Brightness alone tells you nothing about distance unless you already know how bright the object truly is. And for most of history, we had no way of knowing that. The history of measuring the Milky Way is, at its heart, the history of solving that one stubborn problem. The history of learning how to read true distance out of faint and ambiguous light. And the person who finally solved it worked in near silence, in a crowded room full of women, for very little money and almost no recognition at all. In the first years of the 20th century, at the Harvard College Observatory in Cambridge, Massachusetts, there worked a woman named Henrietta Swan Leavitt. She was one of a team of women hired to do the tedious, exacting labor of measuring and cataloging stars from photographic plates. Women who were known at the time, without irony, as computers. They were paid a few cents an hour. They were not permitted to operate the great telescopes themselves. Leavitt was also, for much of her life, profoundly deaf, and bent over her glass plates, examining a particular kind of pulsing star in the faint clouds that hang near our galaxy, she noticed something that would unlock the entire cosmos. The stars she studied are called Cepheid variables, and they do something remarkable. They brighten and dim in a steady repeating rhythm, swelling and shrinking like a slow beating heart. And Leavitt discovered that this rhythm was not random. The longer a Cepheid took to complete its cycle, the brighter it truly was. The relationship was clean, reliable, and mathematical. This is what astronomers had been desperate for across all those centuries. It was a standard candle. If you could measure how long a Cepheid took to pulse, you would know its true brightness. And if you knew its true brightness and could see how dim it appeared from Earth, then the distance to it simply fell out of the comparison. The way you can judge how far away a streetlight is if you already know how bright the bulb inside it burns. Think of what that meant. A woman who could not hear, working for pennies, forbidden from touching the instruments, sitting quietly with plates of glass and the patient light of distant stars, had just handed all of humanity its first true ruler for the universe. Every great measurement that followed was built on the foundation she laid. She rarely received the credit. The cosmos, in a sense, owes her a debt it can never repay. With Leavitt's ruler in hand, the false picture finally began to break apart. Around the year 1918, an American astronomer named Harlow Shapley, working at the Mount Wilson Observatory in the mountains above Los Angeles, used Leavitt's relationship to measure the distances to great spherical swarms of stars called globular clusters, which orbit the galaxy like a halo of glittering bees. When he mapped where those clusters actually sat in space, the result was staggering. They were not centered on the sun at all. They were centered on a point thousands upon thousands of light years away from us, off in the direction of the constellation Sagittarius. The center of the galaxy was over there. We were not at the heart of anything. We were far out toward the edge, sitting quietly in a thinly populated suburb of a structure far larger than anyone had dared to imagine. This was not a small correction. This was a second Copernican wound. Centuries earlier we had learned that the Earth was not the center of the solar system. Now we were learning that the sun was not the center of the galaxy either, that we lived not in the bright crowded core but far out in the dim outskirts, and that the whole thing was vastly bigger than the careful models had ever allowed. How big became the subject of one of the most famous arguments in the history of science. In April of the year 1920, in Washington, two astronomers stood before an audience to debate the scale of the universe itself. On one side stood Shapley, arguing that the galaxy was enormous, and that it was essentially the entire universe. On the other stood a careful astronomer named Heber Curtis, who argued that the galaxy was smaller, but that the faint spiral smudges seen scattered across the sky, the so-called spiral nebulae, were not clouds inside our own galaxy at all. They were separate galaxies, island universes, unthinkably far away. Each man was right about something. Each was wrong about something. And the question of who was correct could not be settled by argument. It could only be settled by measurement. That measurement came just a few years later, and it came from the same mountaintop. Working at Mount Wilson with the great 100-inch Hooker telescope, the largest in the world at the time, an astronomer named Edwin Hubble turned his attention to the largest of the spiral smudges, the Andromeda Nebula. And there, in the photographic plates taken across the nights of 1923 and 1924, he found it. A single Cepheid variable star, pulsing with its telltale rhythm, buried inside the Andromeda spiral. He measured its period. He calculated its true brightness using Leavitt's law. He compared it to how faint it appeared, and the distance that came back was so vast that there could be no argument left. Andromeda was not inside our galaxy. It was a separate galaxy entirely, an island of hundreds of billions of stars drifting at an almost incomprehensible distance from our own. In that single moment, the universe became immeasurably larger, and the Milky Way became immeasurably smaller. Our galaxy was not the universe. It was one island among countless islands, one spiral among uncounted spirals scattered across a cosmos so large that the word itself seems to buckle under the weight of it. We had spent our entire history believing we lived in everything. We had just learned we lived in a single grain among an endless beach of grains. In the centuries since, our tools have grown sharper than anyone in Hubble's time could have dreamed. We have learned to map the unseen parts of the galaxy not with visible light, which the dust blocks, but with radio waves that pass straight through it, listening to the faint hum of hydrogen gas at a wavelength of 21 centimeters, tracing out the great spiral arms hidden behind the fog. We have launched a spacecraft called Gaia, sent up by the European Space Agency in the year 2013, whose only task was to measure, with breathtaking precision, the exact positions and motions of nearly 2 billion stars, building the finest three-dimensional map of our galaxy ever made. And from all of this, the modern answer has slowly come into focus. The Milky Way is a barred spiral roughly 100,000 light-years across, although its true edge is soft and faint, and by some measures it may stretch even wider. The story of how we traced the hidden shape of those arms is itself a quiet triumph. The dust that fills the galaxy's plane blocks ordinary starlight, so for a long time the spiral structure beyond our own corner was little more than a guess. The breakthrough came not from any light our eyes can see, but from radio. In the year 1944, a young Dutch student named Hendrik van der Hulst, working through the long dark nights of the German occupation of the Netherlands, predicted that the vast clouds of cold hydrogen drifting between the stars should give off a faint, steady radio signal at a wavelength of 21 centimeters. Hydrogen is the most common substance in all the universe, and this faint whisper, he reasoned, should be coming from everywhere at once. A few years later, that whisper was found, exactly where he had said it would be. And because radio waves slip straight through the dust that stops visible light, this discovery handed astronomers a way to see the unseeable. Through the 1950s, the Dutch astronomer Jan Oort and his colleagues, along with teams in other countries, began to map the cold hydrogen across the entire sky, listening to its faint hum and using the slight shifts in its pitch to work out how fast each cloud was moving and how far away it lay. Slowly, patiently, cloud by cloud, the hidden architecture of the galaxy emerged out of the fog. The great spiral arms, forever invisible to the human eye, were drawn at last, traced not by what we could see, but by what we had learned to hear. And within that pale wheel of light lies a number of stars so large it resists all understanding. The most careful estimates suggest the Milky Way holds somewhere between 100 billion and 400 billion stars, each one a sun in its own right, a great many of them circled by worlds of their own. Try for a moment to truly feel a number like that. Imagine you set out to count them, one star every second, never pausing to sleep or to eat, counting through every hour of every day and every night. You would not finish in a year. You would not finish in 1,000 years. Counting one star each second without rest, you would need more than 3,000 years simply to reach 100 billion, and several times longer than that to count them all. You would have begun your counting before the first cities were ever built, and you would still be at it tonight, with the greater part of the sky uncounted. And all those suns are bound together in a shape so wide and so thin that its true proportions break the imagination. We tend to picture a galaxy as a great ball of stars, but the Milky Way is nothing of the kind. It is a disk, a flattened wheel far wider than it is deep. If you could shrink the whole galaxy down to the width of a large city, the thickness of its glowing disk would be little more than a sheet of paper laid flat on the ground. At its center sits a swollen, brilliant bulge of older stars, and from that hub, the faint spiral arms wind slowly outward through the flat plain, lanes where new stars are still being born out of collapsing clouds of gas. Seen from far above, it would shine like a vast pinwheel of light turning against the black. And here is the detail that places you, lying there in the dark, inside the picture. Our sun is not at the heart of that pinwheel. It is not anywhere near it. We sit far out toward the rim, roughly 26,000 light-years from the galactic center, tucked inside a minor spiral feature that astronomers call the Orion Arm, a quiet lane caught between two of the galaxy's grander arms. Around and above and below the whole bright disk drifts a vast spherical halo, sparsely scattered with ancient globular clusters, dense knots holding some of the oldest stars in the galaxy, a few of them nearly as old as the universe itself. We are not at the center of anything. We are dwellers in a calm and unremarkable suburb of an ordinary spiral, far from the blazing, crowded core, looking out at the whole structure from the edge of the crowd. This is the structure we are asking about tonight. This is the wheel we want to cross. So now finally, let us feel that number. Let us hold it in the dark for a moment. A light year is the distance that light travels in a single year. And because light moves at nearly 6 trillion miles every year, 1 light year is itself a distance of nearly 6 trillion miles. Now multiply that by 100,000. The galaxy is roughly 600,000 trillion miles across. That is a number so large that writing it out as ordinary figures would fill a line with zeros, and reading it aloud means nothing, because the human mind simply cannot hold a quantity that size. So let us shrink it instead. Imagine taking our sun, a star so large that more than 1,000,000 Earths would fit inside it, and shrinking it down until it was nothing but a single grain of sand resting on your fingertip. At that scale, the very nearest star to us would be another grain of sand resting many miles away across an empty landscape. And the entire galaxy, every star, every world, every drifting cloud of gas, rendered at the scale where the sun is a single grain of sand, would still be a structure roughly the size of a continent. Grains of sand, scattered across a continent of empty dark, with mile after mile of nothing in between each one. And this is the crushing truth that everything tonight will return to. All of human history has unfolded in one tiny, almost perfectly still corner of this structure. Every empire that has ever risen and fallen, every word ever spoken in every language, every life ever lived and lost, all of it has happened in one small motionless seeming patch of a spiral so vast that light, which crosses the entire distance from the Earth to the Moon in a little over 1 second, needs 100,000 years to travel from one side of our home to the other. We have not crossed it. We have barely glanced across it. And we are about to discover just how far beyond our reach that crossing truly lies. To understand just how far beyond our reach this crossing lies, we have to begin with the fastest thing that exists. Not the fastest thing we can build, the fastest thing the universe permits. Because if anything could cross the galaxy quickly, it would be this. And the strange, sobering fact at the heart of tonight is that even this, the absolute speed limit of reality itself, is nowhere near fast enough. That fastest thing is light, and for most of human history, people assumed that light had no speed at all, that it simply appeared everywhere at once, instantly, the moment a candle was lit or the sun rose. It seemed obvious. You open your eyes and the whole room is there. There is no waiting. There is no delay. Light, it seemed, was not something that travelled. It was simply something that was. The first person to prove otherwise did so by watching a distant moon. In the year 1676, a Danish astronomer named Ole Romer was working at the Paris Observatory, carefully timing the moons of Jupiter as they slipped in and out of the giant planet's shadow. There was one moon in particular, the innermost large moon, called Io, that vanished and reappeared like clockwork on a rapid, regular schedule. It should have been perfectly predictable. But Romer noticed something deeply strange. When the Earth was on the near side of its orbit, closer to Jupiter, the eclipses of Io ran early. When the Earth was on the far side, farther from Jupiter, the same eclipses ran late, by many minutes. He realized what this meant, and it was a quiet revolution. The eclipses were not actually changing. What was changing was the distance the light had to travel to reach his eye. When the Earth was farther away, the light from Io took longer to arrive, and so the eclipse appeared to happen later. Light was not instantaneous after all. It had a speed a finite, measurable speed. And though his estimate was rough by modern standards, Romer had done something no one before him had managed. He had caught light in the act of travelling. He had timed the untimable. Romer had shown that light was fast but finite. The task of measuring just how fast, here on the Earth itself, fell to others. In the year 1849, a French physicist named Hippolyte Fizeau devised an ingenious experiment in the hills outside Paris. He sent a beam of light racing toward a distant mirror, miles away across the city, and on its return passed it through the gaps between the teeth of a rapidly spinning wheel. By turning the wheel just fast enough that a returning flash of light was blocked by the next tooth coming around, and knowing exactly how quickly the wheel spun and how far the light had travelled, he could calculate the speed of light for the very first time without ever leaving the ground. His answer came remarkably close to the truth. In the decades that followed, an American named Albert Michelson devoted much of his life to measuring that speed ever more precisely, using mirrors and beams of light sent across carefully measured distances, refining the figure again and again until it was known to extraordinary accuracy. For this lifelong pursuit of light, Michelson became, in the year 1907, the first American ever to win a Nobel Prize in the sciences. Generation by generation, the number grew sharper, until we could state the speed of light with a precision that would have astonished Romer as he stared up at those distant moons. We now know that speed with extraordinary precision. Light travels at very nearly 186,000 miles every second. Not every hour, not every minute, every second. To feel what that means, consider this. In a single second, a beam of light could travel all the way around the entire Earth not once, but more than 7 times. In the time it takes you to say the word now, light has circled the planet 7 times over and started on the 8th. It is a speed so far beyond anything in human experience that our intuition has no place to put it. To grasp the distances we are dealing with tonight, we first have to understand the strange and beautiful unit that astronomers use to measure them. We call it the light year. It sounds at first like a measure of time, but it is not. It is a measure of distance, the distance that a beam of light, moving at that incomprehensible speed, travels in 1 full year. And because light is so fast, that distance is staggering. In a single year, a ray of light covers nearly 6 trillion miles. That is the length of a single light year. 6 trillion miles, the distance light runs while the Earth makes one slow journey around the Sun. Once you hold that idea, the whole sky rearranges itself into a kind of map of time. The Moon, our nearest neighbour in space, lies a little more than 1 light second away, so the moonlight in your window left its surface just over a second ago. The Sun is about 8 light minutes away, which means the sunlight warming the Earth at this very moment began its journey 8 minutes ago, and if the Sun were somehow to vanish, you would go on seeing it shining and feeling its warmth for 8 more minutes before the darkness and the cold arrived. The far planet Neptune, out at the frozen edge of our solar system, is around 4 light hours away, and the very nearest star beyond our own Sun, a faint red ember called Proxima Centauri, lies more than 4 light years from us. Sit with that final leap for a moment, because it is where the human scale finally shatters. From the Sun to the Earth, 8 light minutes. From the Sun to the next nearest star, more than 4 light years. The jump from minutes to years is the jump from your own front garden to a distant inhabited shore across an ocean for which you have no ship. And that is only the very first step into the galaxy. Proxima Centauri is the closest of all the hundreds of billions of stars that make up the Milky Way. The crossing we are asking about tonight does not span 4 light years. It spans 100,000 of them. And yet, here is where the universe truly begins to humble us. We have just watched that blazing speed take whole minutes to carry sunlight to your skin, and more than 4 long years to reach even the nearest star beyond our own. The fastest thing that can possibly exist is not instant after all. It is merely very, very fast. And against the real size of the galaxy, even the fastest thing there is will turn out to be almost nothing at all. So now ask the question that tonight is built around. How long would it take light, the fastest thing that can possibly exist, to cross the entire Milky Way? And here is the first real answer of the evening, the simplest answer, and in some ways the most haunting. The galaxy is roughly 100,000 light years across. A light year is, by its very definition, the distance light travels in 1 year. So light needs 100,000 years to cross from one edge of our galaxy to the other. Not 100,000 hours, not 100,000 days. 100,000 years of the fastest travel that physics allows, with no acceleration needed, no fuel required, moving at the absolute ceiling of the cosmos the entire way. Let that settle. Let it sink in slowly. A beam of light that left the far rim of our galaxy 100,000 years ago, when the very first members of our own species were beginning to spread across the plains of Africa, when there were no cities, no writing, no agriculture, no wheel, would only now be arriving at the opposite edge. The entire arc of human civilization, every story we have ever told ourselves, has unfolded in less time than it takes a single ray of light to cross our home. Now we have to confront a misconception, because almost everyone carries it, and it quietly poisons our sense of what is possible. Ask anyone what the fastest thing in the universe is, and they will tell you without hesitation that it is light, and they will be right. But ask them whether light is fast enough to get us across the galaxy in a reasonable time, and most people will hesitate, and quietly assume that something so unimaginably quick must surely be enough. After all, light is the fastest thing there is. Surely the fastest thing there is can cross anything quickly. That assumption is wrong. Not slightly wrong. Completely and fundamentally wrong. And it is worth understanding exactly why we make it, because the mistake reveals something deep about the way our minds are built. We learn that light is fast by comparing it to things in our daily lives. Light beats a race car. Light beats a jet. Light beats a bullet. Light beats sound itself, which is why we see the lightning long before we hear the thunder. In every comparison our experience offers, light wins so completely that it stops feeling like a speed at all and starts feeling like a kind of magic. And so we file it away in our minds under the heading of infinitely fast, when in truth light is not infinitely fast. It is merely very, very fast against the tiny distances of human life. Here is what must replace that misconception. Speed, by itself, means nothing. Speed only has meaning when you set it against a distance. And the galaxy is a distance so monstrous that it strips the meaning out of every speed we have ever called fast. Against the width of a city, light is instantaneous. Against the width of the Earth, light is breathtaking. Against the width of the solar system, light is merely quick. And against the width of the galaxy, light is slow. Hackingly, mercilessly slow. The fastest thing in the universe, against the true scale of our home, is a thing that takes longer to make the crossing than our entire species has existed. The galaxy does not just exceed our speeds, it redefines the word slow until even light falls beneath it. And there is a deeper cruelty still, one that closes a door we have not even tried to walk through yet. That speed, the speed of light, is not merely the fastest we have observed. It is, as far as all of physics can tell, the fastest that anything with mass can ever possibly go. And in truth, nothing with mass can ever quite reach it at all. This was the great revelation of a 26-year-old patent clerk working in Bern, Switzerland, in the year 1905. His name was Albert Einstein, and in his theory of special relativity, he showed that the speed of light is not just a speed. It is the structural speed limit of the universe, woven into the very fabric of space and time. As any object with mass is pushed faster and faster toward that limit, it grows more and more resistant to going faster still, requiring more and more energy for less and less gain, until reaching the speed of light would demand an infinite amount of energy. An infinite amount. which means it can never be done. So a spacecraft, a ship, a living human being, anything made of matter, is not merely slower than light. It is forbidden from ever reaching light speed at all. The very best we could ever dream of is to creep close to it, agonizingly close, but never to touch it. And even if we somehow could touch it, even if we could ride a beam of light itself across the galaxy, the crossing would still take 100,000 years. The fastest theoretically permitted journey across our home is one that no human being could ever survive to see the end of, made at a speed no object with mass can ever actually reach. But why should this be? Why should the universe set such a hard and final ceiling on speed, and forbid anything made of matter from ever reaching it? The answer reaches into the deepest part of what Einstein discovered, and it is far stranger than a simple speed limit painted on a road. As you push an object faster and faster, closer and closer to the speed of light, it does not simply keep speeding up in the way our everyday intuition expects. Instead, the energy you pour into it begins to make the object harder and harder to push, as though it were growing more and more massive, more and more reluctant to move. The closer you creep toward the speed of light, the more this resistance swells. Each additional sliver of speed demands more energy than the last, and the cost does not climb steadily. It climbs without any limit at all. To actually reach the speed of light, an object with any mass whatsoever would need not a great deal of energy, not an enormous amount of energy, but an infinite amount of energy. More energy than exists in the entire universe. And since there is no such thing as infinite energy, the destination can never be reached. This is the true shape of the wall. It is not a barrier you might one day break through with a stronger engine or a cleverer design. It is woven into the very structure of space and time. Light is able to travel at light speed only because light has no mass to begin with. Everything that does have mass, every ship, every atom, every living traveler, is held forever on the slower side of that line, able to approach it, but never ever to arrive. We have grown so confident about this limit that we have rebuilt our very definitions around it. We no longer measure the speed of light using a fixed length, the way you might measure a runner against a track of known length. We have flipped it entirely. The speed of light is now treated as one of the fixed, unchanging pillars of reality, and we define our unit of length, the meter, by how far light travels in a precise fraction of a second. The speed of light is no longer something we measure. It is now one of the things by which everything else is measured. That is how certain we are. That is how fundamental it has become. Consider what this means for the light reaching your eyes on a clear night. When you look up at a star, you are not seeing it as it is. You are seeing it as it was when its light first left it, however many years ago that was. The light from a star 100 light-years away shows you that star as it existed a century ago. The light from a star on the far side of our galaxy, if you could see it, would show you a star as it was when the last ice age still gripped the world. You can never see the galaxy as it is right now. There is no such thing as right now across these distances. There is only the past, arriving late, layered upon itself, the whole sky a kind of museum of ancient light, each point showing a different moment frozen in transit. There is a vivid example of this hanging in the winter sky. The bright reddish star Betelgeuse, the shoulder of the constellation Orion, lies several hundred light-years from us. This means that the light you see when you look up at it tonight left its surface several centuries ago, around the time of the great sailing ships and the first telescopes. Betelgeuse is old and swollen and nearing the end of its life, and astronomers know that it will one day explode as a brilliant supernova. Here is the strange part. It may have already exploded. The blast may have happened 100 years ago, or 50, or even last year, and we would have no way at all of knowing, because the light and the news of that explosion would still be crossing the long gulf between us, still on its way, not yet arrived. When we finally see Betelgeuse erupt, if we are alive to witness it, we will be watching something that in truth happened centuries ago in our own past. We are not seeing the universe as it is. We are seeing its mail, delivered slowly, some of it written by senders who may no longer be there at all. And so the first honest answer to our question stands before us, cold and clear. If you could become a thing without mass, a pure ray of light, and travel at the absolute fastest speed the universe will ever allow, you would still need 100,000 years to cross from one edge of the Milky Way to the other. That is the flaw. That is the best the laws of physics offer to anything moving through space in the ordinary way. Everything we can actually build, everything made of matter, everything that could carry a living mind, is doomed to be slower than this. Often, as we are about to see, almost unbelievably slower. Because here is the next layer waiting for us in the dark. We have been talking about light, about the impossible ideal. But you are not made of light. Our ships are not made of light. We are made of heavy, stubborn matter, and our fastest machines, the proudest and swiftest objects human hands have ever forged, do not move at 186,000 miles per second. They move at a tiny, crawling fraction of that. And when we set those real machines, our genuine triumphs of engineering, against the true width of the galaxy, the result is not measured in thousands of years. It is measured in something far longer, something that dwarfs the age of the human story so completely that the comparison begins to feel less like science and more like a kind of vertigo. That is where we turn next, to the fastest things we have ever actually made, and to the crushing arithmetic of what they could truly do. For almost the entire span of human existence, the fastest a person could possibly travel was the speed of a galloping horse. For roughly 200,000 years, across every continent and every civilization, no human being ever moved faster than an animal could carry them. Perhaps 25 or 30 miles in a single hour, and only in brief, thundering bursts before the animal tired. Kings and beggars alike were bound by the same limit. The fastest message, the fastest army, the fastest escape, all of it moved at the pace of hooves on Earth. That was the ceiling of human velocity for almost the whole of our story, and it held without challenge for 1,000 generations. Then, in a span of time so short it barely registers against that long stillness, everything changed. In the early 1800s, the steam locomotive arrived, and for the first time human beings were carried across the land by something other than muscle. A famous early engine, built by the engineer George Stephenson and tested in England in the year 1829, could manage around 30 miles per hour, and people genuinely feared that travelling at such a speed might be fatal to the human body. They were wrong, of course, but the fear tells you how violently that machine had shattered a limit that had stood since before recorded history. From there the ceiling rose with dizzying speed. The automobile pushed past the horse and kept climbing. And then, on a cold morning in December of the year 1903, on the windswept dunes of Kitty Hawk in North Carolina, two brothers named Wright lifted a fragile machine of wood and cloth into the air and held it there for a few seconds. That first flight crept over the ground more slowly than a running man, and yet within a single human lifetime, the descendants of that flimsy craft would be tearing through the sky faster than sound itself. That barrier fell on the 14th of October in the year 1947, high above the California desert. A test pilot named Chuck Yeager, flying a bullet-shaped rocket plane, pushed through the speed of sound for the first time, traveling at roughly 700 miles per hour. The sky cracked with a sound like thunder, the sonic boom, as he tore through a wall that many engineers had feared was solid and deadly. A speed that would have seemed like pure fantasy to anyone living only a century before had become a thing a single brave man could do in an afternoon. And still we climbed. To leave the ground was no longer enough. We wanted to leave the Earth entirely. To reach orbit, a spacecraft must travel at roughly 17,000 miles per hour, fast enough that as it falls toward the Earth, the ground curves away beneath it just as quickly, so that it falls forever without ever landing. And to escape the Earth completely and journey to the Moon, our machines pushed faster still. The fastest any human being has ever traveled came during the Apollo program, when the crew of one returning mission in the year 1969 came home from the moon at a speed of nearly 25,000 miles per hour. That remains the record. No human heart has ever beaten while moving faster than that. 3 men, falling back toward the Earth inside a small charred capsule, hold the title of the fastest humans who have ever lived. But our unmanned machines have gone faster yet, far faster, because they do not have to keep a fragile crew alive. In the year 1977, we launched a spacecraft called Voyager 1, a small robotic explorer that toured the outer planets and then simply kept going, outward and outward, until in the year 2012 it became the first human-made object ever to cross into interstellar space, leaving the protective bubble of our sun behind. It is, right now, the most distant object human hands have ever made, drifting silently through the dark at a speed of roughly 38,000 miles per hour. It has been traveling for decades. It will travel for tens of thousands of years more. And then there is the fastest of them all. In the year 2018, we launched a probe called the Parker Solar Probe, named after a living scientist for the first time in the history of such missions, a man named Eugene Parker who had spent his life studying the sun. This probe was designed to do something audacious, to dive again and again toward the sun, swinging closer to its blazing surface than anything we had ever sent. And each time it falls inward, the sun's immense gravity flings it forward to an almost unbelievable velocity. At its closest approach, in the final days of the year 2024, the Parker Solar Probe reached a speed of roughly 430,000 miles per hour. It is the fastest object human beings have ever made. And here is the detail that matters most. It did not reach that speed by burning fuel. It reached it by falling, by stealing energy from the sun's gravity and from the gravity of Venus, in a long and patient dance. Pure engine power could never have done it. It is worth pausing on that strange trick, the gravity assist, because it is the only thing that has let our machines climb as high as they have. When a small spacecraft falls toward a massive planet and swings closely around it, it can steal a tiny portion of that planet's own motion through space and fling itself onward faster than it arrived, without burning a single drop of fuel. The planet, in turn, is slowed by an amount so vanishingly small it could never be measured. It is a kind of cosmic theft in which the victim never feels the loss. A spacecraft lighter than a car borrows speed from a world thousands of times more massive than the Earth and races away enriched. Every one of our fastest probes has leaned on this trick, slingshotting past planet after planet, gathering velocity in patient stages across years and even decades. This is how, in the year 2015, a piano-sized probe called New Horizons came racing past the distant frozen world of Pluto after a voyage of more than 9 years and 3 billion miles, having flung itself off the giant planet Jupiter along the way to steal a little extra speed. And it is how the Parker Solar Probe reached its record, not in one great burst of power, but by falling toward the sun again and again, each pass tightening its orbit and quickening its pace. And yet, even with every trick we possess, look at how far short we still fall. The Parker Solar Probe, the fastest object human hands have ever built, racing along at 430,000 miles per hour, is still moving at less than 1/1500th of the speed of light. Turn that around, and the cruelty of it becomes plain. Light is more than 1,000 times faster than the swiftest thing we have ever made, and we have already seen that light itself, that 1,000 times faster traveller, would still need 1,000 centuries to cross the galaxy. Our greatest machine then, set loose at its top speed and aimed at the far rim, would arrive not in 1,000 centuries, but in something closer to 150 million years. The crossing does not merely exceed a human life, it exceeds the entire age of our species many thousands of times over. That detail points to the central wall standing between us and the stars, a wall made not of distance but of arithmetic. It is called the rocket equation, and it was first written down by a self-taught Russian schoolteacher named Konstantin Tsiolkovsky in the year 1903, the very same year the Wright brothers first flew. The equation describes a cruel and inescapable truth about rockets. To go faster, you must carry more fuel, but the fuel itself has weight, and so you must carry even more fuel just to push the fuel you already have. And that additional fuel has weight too, demanding still more fuel to move it. The relationship is not gentle. It is not a matter of adding a little more for a little more speed. It is exponential. Each increase in your final speed requires a wildly, savagely larger amount of fuel than the last. This is the tyranny that chains us to our crawling pace. To reach even a small fraction of the speed of light using ordinary chemical rockets, the kind that have carried every astronaut who has ever flown, you would need an amount of fuel that defies all sense. Not a few times the mass of the ship, not 100 times. To reach a meaningful fraction of light speed by burning chemical fuel, you would need a quantity of fuel so vast that it exceeds anything in our solar system. Not the mass of the Earth, not the mass of the Moon and every planet combined, not the mass of the Sun itself. There is not enough chemical fuel in the entire mass of every object circling our star to push a single ship to the speeds that interstellar travel would truly require. The equation simply forbids it. The harder you push against the speed of light with ordinary engines, the more impossibly the cost explodes, until the dream collapses under its own arithmetic. Faced with this wall, the brightest minds of the last century did not simply give up. They asked whether some other kind of engine, something far more powerful than the burning of chemical fuel, might break the tyranny of the equation. And they arrived at ideas that are real, that were studied with great seriousness, and that still fall heartbreakingly short. In the late 1950s, a team of physicists in the United States, among them the brilliant Freeman Dyson and the mathematician Stanislaw Ulam, designed something they called Project Orion. The idea was almost unthinkable in its boldness. The ship would be driven forward by detonating a long series of nuclear bombs behind it, one after another, each blast slamming against a massive shock plate and kicking the vessel to higher and higher speeds. It sounds like pure madness, and yet the mathematics held together. A nuclear pulse ship of this kind could, in principle, reach speeds far beyond any chemical rocket, perhaps a few % of the speed of light. But even that, even riding a long chain of nuclear explosions, would still take many centuries to reach the nearest star, and tens of millions of years to cross the galaxy. Other ideas are gentler, and some already fly. Ion engines, which push a ship forward by hurling out a thin stream of electrically charged particles, run aboard real spacecraft today. A NASA probe called Dawn used one to visit distant worlds in the asteroid belt after its launch in the year 2007. These engines are astonishingly efficient, but their thrust is feather soft, building speed across years rather than minutes. They are wonderful for crossing the solar system. They remain hopelessly inadequate for crossing the galaxy. Every real engine we have ever built or seriously designed, from the chemical to the nuclear to the ionic, runs sooner or later into the same ancient wall. So let us now do the cruel calculation that this whole section has been building toward. Let us take our fastest machine, the Parker Solar Probe, moving at its record speed of 430,000 miles per hour, and let us pretend, generously, that it could somehow hold that speed forever, even though in reality it only touches that velocity for a brief moment at the bottom of its dive toward the sun. Now point it at the galaxy and let it fly. How long would the fastest object humanity has ever built take to cross the Milky Way? The answer is roughly 150 million years. 150 million years, at the speed of our greatest triumph, held steady the entire way. To feel what that number means, consider this. 150 million years ago, there were no humans, no apes, no creatures resembling us in any way. The Earth was ruled by dinosaurs. If the Parker Solar Probe had launched on its galactic crossing back then, carrying some impossible immortal passenger, That passenger would have watched the age of the dinosaurs reach its height and then end in fire. They would have watched mammals rise from small scurrying creatures into whales and elephants, and eventually into us. They would have watched entire mountain ranges lift from the sea and erode back into dust. They would have watched continents drift across the face of the earth. And after all of that, after 150 million years of the fastest travel we have ever achieved, they would still only just now be reaching the far side of our galaxy. And the Parker probe is the exception, the absolute pinnacle. Our other machines are far slower, and so the numbers grow far worse. Voyager 1, our brave interstellar wanderer, moving at 38,000 miles per hour, would need nearly 2 billion years to cross the galaxy. 2 billion years is close to half the entire age of the Earth itself. And if you imagine simply driving across the galaxy at the speed of a car on a highway, around 60 miles per hour, the journey would take more than 1 trillion years. A trillion years is so much longer than the current age of the universe that the universe would have to live out its entire history so far, from the first instant after its birth to this very moment, roughly 70 times over, before you completed the drive. You would run out of universe long before you ran out of road. To feel the true weight of these numbers, try to hold just one of them in your mind. 150 million years, the time it would take our fastest probe to cross the galaxy. Turn that span backward into the past, and you find yourself in the age of the dinosaurs, in a world that would be utterly unrecognizable to you. The continents sat in different places. The Atlantic Ocean was only beginning to open. Strange great reptiles moved through warm forests beneath a sky that held the same sun and the same galaxy, but almost nothing else you would know. If a ship had launched from that ancient Earth at the speed of the Parker probe, aimed at the far side of the galaxy, it would only now, after all that immense stretch of time, be arriving, and turn the same span forward into the future, and the vertigo only deepens. 150 million years from now, the continents will have drifted into shapes no map could predict. The creatures alive today, very probably including our own kind, will be long gone, replaced by others we cannot begin to imagine, or by nothing at all. Mountains will have risen and worn away again into plains. And through all of that unimaginable change, a single ship launched today at our greatest speed would still be in transit, still crossing, not yet arrived. That is what it truly means to set even our fastest machine against the width of the galaxy. The journey does not merely outlast a person. It outlasts whole species. It outlasts continents. It outlasts the very face of the world. This is the crushing reality of our machines. Every speed record we have ever celebrated, every triumph of engineering from the locomotive to the rocket to the probe diving into the sun, every single one of them, set against the true width of the galaxy, is essentially standing still. The difference between a galloping horse and the fastest spacecraft ever built, a difference that represents the entire arc of human technological achievement, the difference between hooves on dirt and a probe kissing the surface of the sun, makes almost no difference at all to the galaxy. Both are crossing times measured in unthinkable spans. Both are, against this scale, a kind of stillness. We have spent our whole history learning to go faster, and we have gone breathtakingly faster, and it has bought us, against the galaxy, almost nothing. So if light is too slow, and our fastest machines are very nearly motionless against this scale, it would seem that the verdict is in. The galaxy cannot be crossed, not by light, not by rockets, not by anything we can build or imagine. The distances are simply too vast, the speeds too forbidden, the arithmetic too cruel. The honest conclusion, drawn from everything we have explored so far, is that a crossing of the Milky Way within any human timescale is flatly, permanently impossible. And that conclusion would be correct, completely correct, if time were the simple, steady, universal thing we all feel it to be. If a year were truly a year for everyone, everywhere, no matter how fast they moved, then the case would be closed, and we could end our journey here in quiet defeat. But time is not what you think it is. Time is not fixed. Time is not universal. Time bends, and hidden inside the very same physics that forbids us from reaching the speed of light lies a loophole so profound, so deeply strange, that it changes the entire question. Because while a crossing of the galaxy may take 100,000 years as measured by the clocks back home, it does not have to take 100,000 years for the traveler. For the one who actually makes the journey, the crossing could, in principle, take a single human lifetime, or less, far less. And to understand how that can possibly be true, we have to dismantle everything you think you know about time itself. Everything you feel about time is a kind of comfortable illusion. You feel that time flows at a single, steady rate, the same for everyone everywhere, ticking forward identically whether you are sitting still in a chair or hurtling through the sky in an aircraft. A second feels like a second. An hour feels like an hour. And in the small, slow world of human experience, that feeling is close enough to true that we never notice the cracks. But the cracks are there. Time does not flow at a single rate. Time is not the same for everyone. The faster you move through space, the slower you move through time. And this is not a trick of perception or a philosophical riddle. It is a measured, verified, concrete fact about the universe. And it is the key that unlocks the entire question of crossing the galaxy. This was the second great gift of that young patent clerk in Bern. In the year 1905, Albert Einstein began with a single strange assumption, an assumption that seemed to make no sense at all. He assumed that the speed of light is the same for every observer, no matter how they are moving. This sounds harmless until you think it through. Imagine you are running toward a beam of light. Common sense says the light should appear to approach you faster, the way an oncoming car seems faster when you drive toward it. But the universe does not work that way. No matter how fast you run toward a beam of light, no matter how fast you flee from it, you will always measure that light moving at exactly the same speed. The light does not care about your motion at all. For the speed of light to stay fixed for everyone like that, something else has to give. And what gives is time and space themselves. If the speed of light cannot change, then the very rate at which your clock ticks and the very length of the ruler in your hand must change instead, bending and stretching to keep the speed of light constant for every observer. This is the heart of special relativity. Time and space are not the rigid, unchanging stage on which events play out. They are flexible. They warp, and the warping depends on how fast you move. The faster you travel through space, the more slowly your time unfolds compared to someone standing still. Now, this is the kind of claim that deserves suspicion, because it sounds like fantasy. But it has been tested again and again with growing precision, and it has passed every test. The most charming of these tests took place in the year 1971. Two scientists, Joseph Hafele and Richard Keating, took extraordinarily precise atomic clocks, the most accurate timekeepers ever built, and simply flew them around the world aboard ordinary commercial airliners, while leaving identical clocks behind on the ground. When the flying clocks came home and were compared to the ones that had stayed still, they disagreed. The clocks that had flown had ticked a slightly different amount of time than the clocks that had remained on the ground. The difference was tiny, measured in fractions of a millionth of a second, but it was exactly what Einstein's mathematics had predicted. Time really had passed at a different rate for the clocks that moved, and this is not some delicate laboratory curiosity with no bearing on real life. Every time you use the navigation in your phone or your car to find your way, you are relying on satellites high above the Earth, and those satellites move so fast and sit so high that their clocks tick at a measurably different rate than the clocks on the ground below. If engineers did not constantly correct for this slippage of time, the navigation system would drift further and further from the truth, and within a single day it would place you miles away from where you actually stood. Time dilation is not a theory we keep in a drawer. It is a thing we engineer around every hour of every day, quietly, in the machines we have built and now depend upon. There is an even more elegant proof falling through the sky above you at this very moment. When particles from deep space slam into the top of our atmosphere, they create tiny, short-lived particles called muons. These muons decay so quickly that by all rights they should vanish long before they reach the ground far below. And yet they reach the ground in great numbers. The reason is that they are moving so fast that their internal clocks slow down dramatically, stretching their brief lives just long enough to complete the fall. The universe is showering us constantly with tiny travelers whose time has been bent by their speed, and we can catch them and count them and confirm, over and over, that time slows for the swift. So now return to our question and watch how it transforms. When we said that crossing the galaxy takes 100,000 years, we were not telling the whole truth. We were telling the truth as measured by clocks back home, clocks resting quietly on the Earth, watching the journey from a distance. That is the answer in the home frame, and it never changes. From the perspective of everyone left behind, the crossing always takes at least 100,000 years. But the traveller is not standing still. The traveller is moving, and moving fast, and so the traveller's clock does not agree. For the one who actually makes the journey, far less time passes, and the closer they push toward the speed of light, the more violently their time slows, until the gap between the two clocks becomes almost unbelievable. Here is how extreme this effect becomes. If you could travel at 99% of the speed of light, time aboard your ship would slow to roughly 1/7 of the rate it passes on Earth. Push to 99.99% of light speed, and your time would slow to around 1/70th of the home rate. And the closer you creep toward that ultimate limit, the more dramatically the gap widens, with no ceiling. There is no maximum to how much time can stretch. As you approach the speed of light, the years aboard your ship can compress into months, the months into days, the decades of the outside world folding down into a span a single human could live through. The faster you go, the shorter your own crossing becomes, even as the crossing seen from home stays exactly as long as it always was. To make this strange stretching of time feel real, imagine two twins born in the very same hour, who say goodbye to one another as grown adults. One of them boards a ship and races out toward the stars at very nearly the speed of light, travels for what feels to them like only a handful of years, then turns around and comes home. The other simply stays on Earth and lives an ordinary life. When the traveller returns and steps off the ship, barely older than the day they left, they find their twin transformed. The one who stayed has aged decades. The hair has gone white, the children have grown tall. Perhaps the stay-at-home twin has already died of old age while the traveller was still young. They were born in the same hour. They are no longer anywhere near the same age, and neither of them did anything wrong. Time itself simply ran at different rates for the two of them. You might wonder why it is the traveller who stays young rather than the other way around, since motion ought to be relative, and each twin sees the other moving away. The resolution lies in the fact that their two journeys are not the same. The twin who leaves must speed up, turn around, and slow down again, feeling the push of that acceleration in their body the whole way. The twin who stays feels none of it, resting quietly in one unbroken frame. That difference, the bending and turning of one path against the straightness of the other, is what breaks the symmetry and decides without any doubt which of them comes home the younger. There is also the question of what such a journey would even look like from inside the ship, and the answer is its own quiet marvel. As you approach the speed of light, the stars ahead of you would seem to crowd together toward the point you are racing toward, gathering into a bright ring in the direction of your flight, while the space behind you fell dark and empty. Their colours would shift as well, the light ahead turning bluer and fiercer, the light behind dimming away toward red and then toward nothing. The familiar sky would warp into something no human eye has ever beheld, the entire universe seeming to funnel itself into the narrow road ahead of you. It is worth saying plainly that some imagine other ways across, ways that would sidestep all of this. There are theoretical ideas, drawn from the deepest mathematics of Einstein's work, of bending space itself so that a ship might travel faster than light without ever locally breaking the cosmic speed limit. or of tunnels through space called wormholes that might join two distant points directly. These remain, for now, pure speculation. We have never built such a thing, never observed one, and may discover they are forbidden by laws we do not yet fully understand. They live, at present, in the realm of equations and dreams, not engineering. It is worth being honest, too, about the price of the one road we know to be real, the time dilation loophole itself. Bending time by travelling at nearly the speed of light is not forbidden by physics. We have measured it happening. But to actually push a ship to those speeds, and then to slow it down again at the far end, would demand an amount of energy that staggers the mind, far beyond anything our civilization can presently command. Even if we set chemical fuel aside entirely and imagine the most concentrated fuel that physics allows, a fuel made of antimatter, which releases all of its energy completely when it touches ordinary matter, the numbers remain crushing. To accelerate a starship to a speed where time bends generously, and then to break it back down to rest at the destination, you would need a quantity of antimatter fuel many times the mass of the ship itself. And antimatter is not something we can mine or gather. Every last scrap of it must be manufactured, one tiny particle at a time, in enormous machines, at a staggering cost. All the antimatter that humanity has ever made, gathered together into one place, would not be enough to keep a single household light burning for more than the briefest moment, let alone fling a ship across the stars. So the loophole is genuine. The door of time dilation truly does open, but the key to that door is an amount of energy so vast that for now and very likely for a long age to come, it stays far beyond our grasp. The physics permits the journey, the engineering as yet does not. And there is one last strange consequence of this bending of time. One final thing to consider before we turn away from the loophole entirely. Imagine, despite everything we have said, that such a ship could somehow be built, and that you were aboard it, crossing the galaxy in what felt to you like only 20 years. During those 20 short years of your one life, a full 100,000 years would unfold in the universe outside. Think carefully about what that would mean for what you saw. If you could watch the worlds you swept past, the stars and any planets that circled them, you would not see them moving at their ordinary patient pace. You would see them racing. Civilizations, if any were out there at all, might rise and flourish and crumble in what felt to you like a single passing season. Stars would visibly age before you. The slow, majestic turning of the galaxy itself would seem to quicken. You would become a traveler not only through space but through time, watching the deep future of the cosmos play out in fast motion, compressed and hurried, while your own heart beat on in its ordinary, unhurried rhythm. It is a vision of profound loneliness and profound wonder, held together in a single breath. You would stay young while everything you looked upon grew ancient. You would carry your own small slice of slow human time across an entire galaxy that was busy living out 1,000 centuries around you, and there would be no way to reach back. Any message you tried to send home would crawl outward at the speed of light, taking tens of thousands of years to arrive, reaching a world that had forgotten your name long before the signal landed, if anyone remained there to hear it at all. You could watch their future unfold. You could never speak into it. The connection runs one way only, like everything else about this strange and final road. And so even the loophole, the one true escape we have found from the tyranny of distance, comes wrapped in the very same sorrow that has shadowed every answer tonight. You may cross the galaxy within a single lifetime, but you may do it only once, and only forward, and only alone. The door of time opens for the traveller. It simply never, ever opens back. This is the loophole. This is the strange door hidden inside the laws that seem to lock us out. Let us walk through it with a concrete, gentle journey. Imagine a ship that can accelerate at a steady, comfortable rate, exactly the rate at which you feel gravity pull you toward the floor as you stand on the earth right now. This would be a pleasant ship to live aboard, because the constant acceleration would feel exactly like ordinary weight. You would walk its corridors as though walking on solid ground. Now let this ship accelerate at that gentle rate for the first half of the journey across the galaxy, speeding up and up and up, drawing ever closer to the speed of light. Then, at the halfway point, let it turn around and decelerate at the same gentle rate for the second half, slowing down so it can arrive rather than streaking past. A comfortable, steady push the whole way across. How long does that crossing take? From the perspective of the Earth, of course it takes a little over 100,000 years, because nothing can truly beat light, and the galaxy is 100,000 light years wide. But aboard the ship, for the travelers themselves, the journey across the entire Milky Way would take only a little over 20 years. 20 years. A young person could board that ship at one edge of the galaxy, live through the long, quiet voyage, and step off at the far side still in the prime of life, having aged just over 2 decades, having crossed 100,000 light years of space. The crushing distance that defeated light and defeated our rockets does not defeat a clock that has been slowed by motion. To the traveler, the galaxy shrinks. The distance itself contracts ahead of them, the light years compressing in the direction of travel, until the impossible crossing becomes the work of a single chapter of a life. But here is the price, and it is a price beyond any money, beyond any fuel, beyond any engineering. The traveler crosses in 20 years. The universe outside does not. While the traveler ages 2 decades, 100,000 years pass for everyone they left behind. Consider what this truly means. You step aboard the ship. You wave goodbye to everyone you have ever known and everything you have ever loved. You make the crossing. You age 20 years. And when you arrive, every person you said goodbye to has been dead for 1,000 centuries. Your language no longer exists. Your civilization has risen and fallen, and perhaps risen and fallen many times over. The world you left is as distant to the people of your arrival as the very first cave painters are to us, and more distant still. You have not travelled across space alone. You have travelled across time, into a future so far ahead that nothing of your origin remains. This is the deep asymmetry at the heart of such a journey, and it is the reason the question always comes back to whose clock you are reading. It is sometimes told as a story of 2 people, 2 friends, one who stays home and one who makes the voyage. The traveller returns younger than the friend who stayed. Both clocks were correct. Both lived every second they experienced, but they experienced different amounts of time, because the traveller took a different path through the universe, a path bent by speed, and there is no way to reconcile the two, except to accept that time is simply not the shared and steady river we imagine it to be. The one who moves pays in years they never get to live. The one who stays pays in the loss of the one who left. So we have found our answer, the true and astonishing one. The crossing of the galaxy is possible within a human life. Not in the home frame, never in the home frame, but in the frame of the traveller, the only frame the traveller ever experiences. The door is open. The galaxy can be crossed. A living mind could, in principle, see one edge of the Milky Way at the start of a voyage, and the far edge at its end, having aged only a couple of decades in between. This is not science fiction. This is the honest consequence of the most thoroughly tested physics we possess. The distance was never truly the wall. Time was. And time, unlike distance, can be bent. And yet, the door that opens forward does not open back. The traveller can never return to the time they left, only ever to a future grown unrecognisably old. And there is more standing between us and that journey than the heartbreak of arriving in a forgotten age. Because to reach the speeds that bend time so generously, you must contend not only with the impossible arithmetic of fuel we have already seen, but with new dangers. Dangers that grow more violent the faster you go. Dangers hidden in the very emptiness of space itself. The near-empty void between the stars, which seems so harmless, becomes lethal at these velocities, and the galaxy you are trying to cross is not even holding still while you cross it. It is turning, vast and slow, a moving target that your aim could never quite catch. Those are the hazards waiting in the deeper dark, and we turn to them now. The space between the stars looks like perfect emptiness. When we picture interstellar travel, we imagine gliding through an absolute void, a frictionless nothing where a ship could coast forever undisturbed. And in ordinary terms, that picture is almost right. The space between the stars is emptier than the finest vacuum we can create in any laboratory on Earth. But almost empty is not the same as empty, and at the speeds that bend time in our favour, the difference between almost empty and truly empty becomes the difference between a smooth voyage and a slow execution. Consider just how thin that interstellar medium is. A single cubic centimetre of the air around you right now, a volume smaller than a sugar cube, contains roughly 25 billion molecules, a number so large it strains the imagination, all of them jostling and colliding in a dense invisible crowd. Now take that same small volume out into the deep space between the stars. There, that same cubic centimetre might contain a single atom, just one. A lone hydrogen atom drifting in a darkness so vast and so empty that it would seem to pose no threat to anything. And at ordinary speeds, it poses none. You could drift through it for ages and never notice. But now imagine slamming into that medium at nearly the speed of light. Suddenly those lonely, harmless atoms are not drifting gently past you. They are striking the front of your ship at almost the full speed of light, one after another, a relentless sleet of particles, each carrying enormous energy because of the violence of the impact. At these speeds, a thin scattering of hydrogen atoms stops behaving like a near vacuum and starts behaving like a stream of radiation, a continuous beam of high-energy particles bombarding the leading face of the ship and everything inside it. The faster you travel, the more savage this bombardment becomes. The very speed that shrinks your journey and slows your clock is the same speed that turns empty space into a wall of invisible fire, and it is not only the gas. Scattered through that medium are tiny grains of dust, far smaller than a grain of sand, particles so small you would never see one. At ordinary speeds, harmless. At nearly the speed of light, a single one of those microscopic specks carries the energy of a far larger and faster object, striking the ship with a violence out of all proportion to its size. The faster you push toward light speed, the more each tiny mote becomes a weapon. To survive such a crossing, a ship would need shielding of a kind we can barely imagine, a great barrier of matter held out in front to absorb the endless onslaught, itself slowly eroded and battered by the very void it passes through. There is a final, almost poetic cruelty hidden in this. The entire universe is bathed in a faint afterglow left over from its birth, a whisper of radiation that fills all of space at a temperature just barely above the coldest possible cold. Normally this glow is utterly harmless, far too feeble to feel or to fear. But as you accelerate toward the speed of light, the light coming at you from ahead gets crushed and shifted upward in energy, the gentle radiation hardening into something fierce. Push fast enough, and even that ancient gentle afterglow of creation, the softest light in all the cosmos, would shift forward into a blinding, lethal glare directly ahead of your ship, a furnace built from the leftover warmth of the universe itself. The void is not the friend we imagine. The faster you flee across it, the harder it pushes back, and the emptiness you must cross is not even uniform. By a quiet stroke of fortune, our sun sits inside a region of unusually thin gas, a vast cavity in the interstellar medium that astronomers call the local bubble, blown clear long ago by ancient exploding stars. We happen to drift through one of the emptier corners of the galaxy, but a journey across the whole Milky Way would not stay in such gentle territory. It would carry you, sooner or later, into far denser places. Scattered through the spiral arms are enormous cold clouds of gas and dust, called giant molecular clouds, some of them many light years across, and thousands of times denser than the thin medium around us now. These are the nurseries where new stars are born, dark and frigid and immense. To us, even the densest of these clouds would still seem like a near-perfect vacuum. You could walk through one and feel nothing at all. But to a ship racing at nearly the speed of light, that faint thickening of the gas would be like slamming from open air into deep water. The sparse atoms that were merely dangerous in the empty stretches would become a withering storm. The crossing, then, is not a single steady hazard but a shifting one, gentler where the void is thin, and far more murderous wherever the galaxy gathers its gas into clouds. There is no safe lane that runs clear the whole way across. The danger simply rises and falls along the length of the road. But suppose you solved all of that. Suppose you built the impossible shield and carried the impossible fuel and accepted the heartbreak of arriving in a forgotten future. There would still be one more problem, and it is one that almost no one ever thinks about. The galaxy is not holding still while you cross it. It is turning. The Milky Way is not a fixed and frozen map of lights waiting patiently for you to traverse it. It is a great slow pinwheel, an enormous spinning disk of hundreds of billions of stars, all of them sweeping around the center in vast circular orbits, including our own sun, including the very ground you imagine launching from. Recall the number we began with tonight. Our sun, carrying the Earth and you with it, is racing around the center of the galaxy at roughly 500,000 miles per hour. At that tremendous speed, it still takes our sun more than 200 million years to complete a single orbit, a span sometimes called a galactic year. The sun has lived for around 4.5 billion years, which means that in its entire existence, it has made only about 20 of these great loops around the galactic center. The dinosaurs, who ruled the Earth for so unimaginably long, lived for less than a single galactic year. The whole of human civilization is a tiny fraction of a single degree of one such orbit. The galaxy turns so slowly that on any human timescale it seems frozen. But it is not frozen. It is wheeling steadily through its vast rotation, and over the timescales of a galactic crossing, it moves enormously. We know this turning is real, and we can measure it with great care by watching the light of the stars and the gas between them. As objects move toward us or away from us, their light is subtly shifted, compressed when they approach and stretched when they recede, just as the pitch of a passing siren rises and then falls. By measuring these shifts across the galaxy, especially in the faint radio hum of hydrogen gas that fills the spiral arms, we have mapped the great rotation of the Milky Way, and the spacecraft Gaia, with its precise measurements of the positions and motions of billions of stars, has traced that slow turning in extraordinary detail, revealing a galaxy in constant, majestic motion. So think about what this means for your crossing. Even if you could make the journey in 20 years of your own time, 100,000 years would still pass in the galaxy at large, and in 100,000 years the stars have moved. A star you aimed for at the start of your journey will not be where you aimed. The far side of the galaxy will have rotated onward, the whole pattern of the spiral arms having shifted and swung. You cannot navigate to where a star is. You can only navigate to where it will be, after the long turning of the galaxy has carried it onward through its orbit. The galaxy is a moving target, every part of it sliding along its own great circular path, and any true crossing must account for the fact that the destination is itself in motion, drifting steadily across the dark even as you reach toward it. And here the galaxy reveals one of its deepest and strangest secrets, hidden inside the way it turns. When astronomers carefully measured how fast stars orbit at different distances from the galactic center, they expected a familiar pattern. In our solar system, the planets close to the sun race around quickly, while the distant ones crawl, slowing down the farther out they go, because the sun's gravity weakens with distance. The galaxy, it seemed, should do the same. The stars far out in the thin outskirts, where we live, should orbit far more slowly than the stars packed near the bright center, but they do not. In the late 1960s and into the 1970s, an American astronomer named Vera Rubin, working with a colleague named Kent Ford, measured the rotation of galaxies with unprecedented care and found something that should not have been. The outer stars were not slowing down, They were sweeping around just as fast as the inner ones, far faster than the visible matter could possibly explain. There was not enough gravity from the stars and gas we could see to hold those swift outer stars in their orbits. By all rights, moving that fast, they should have been flung away into intergalactic space long ago. Something unseen was holding them, some vast reservoir of invisible mass, gripping the galaxy with a gravity we could measure but could not see. This was the evidence, building upon a suspicion first voiced by the astronomer Fritz Zwicky back in the year 1933, that most of the matter in our galaxy is not the kind we can see at all. The glowing stars, the shining gas, everything that gives the Milky Way its light, is only a small fraction of what is truly there. Surrounding and permeating the whole galaxy is a vast, invisible halo of what we now call dark matter. A substance that does not shine, does not block light, does not interact with anything in any way we can easily detect, and yet outweighs all the visible stars and gas several times over. The galaxy you are trying to cross is, by mass, mostly a thing you cannot see. The bright spiral we picture is merely the glowing tracer caught inside a far larger cloud of dark, silent mass, a ghost galaxy holding the visible one in its grip. There is a further strangeness to the great spiral arms themselves, one that quietly overturns the natural assumption about them. When we see a photograph of a spiral galaxy with its graceful glowing arms winding out from the center, it is tempting to think of those arms as fixed structures, like the unchanging spokes of a wheel, made of the very same stars year after year, but they are not. The spiral arms are not solid objects at all. They behave more like waves, regions where the orbiting stars and gas briefly crowd together as they pass through, much as cars on a highway bunch into a slow-moving knot of traffic, even though each individual car keeps driving on through and out the other side. The stars do not stay in the arms. They drift through them, lingering a while in the crowd before continuing along their own long orbit. The arm itself is a pattern, a density wave moving through the disk, and the bright young stars that trace its shape are simply the ones briefly lit up by the crowding as they pass. And the turning of the galaxy is not even the whole of its motion. The entire Milky Way is itself adrift, falling through the dark toward its neighbors. The largest of those neighbors is another great spiral, the Andromeda Galaxy, a vast wheel of perhaps 1 trillion stars lying about 2.5 million light-years away, and it is not staying where it is. It is falling toward us, and we toward it, across the emptiness between, closing the gap at something like 250,000 miles per hour. In roughly 4.5 billion years, the two galaxies are expected to meet and slowly tear through one another, their stars sweeping past in a long gravitational dance that will, over hundreds of millions of years, merge them into a single vast new galaxy. The very thing you are trying to cross is not only spinning beneath you, it is sailing toward a collision in the deep future, carrying you and every star you can see along with it, into a sky that will one day hold two galaxies pouring into one. So consider, now, the true nature of the thing we have been trying to cross. It is not a still and simple map of lights. It is a living, turning structure, hundreds of billions of stars sweeping around a center in orbits that take hundreds of millions of years to complete, the whole of it embedded in a vast invisible body of dark matter that we can feel by its gravity, but never see. To cross it is not to travel across a painted ceiling of fixed stars. It is to thread your way through a slowly spinning storm, while the near-empty void tries to cook you with its own thin substance turned to fire, while your destination drifts steadily onward, while most of the matter around you remains forever hidden from your eyes. The galaxy is not a place you pass through. It is a process you must move within, a thing in motion, alive with rotation, far stranger and far more hostile than the quiet band of light in the sky ever let us suspect. And yet the dream does not quite die here either, for even with all of this, the cooking void, the turning galaxy, the invisible dark, there are still those who look at the timescales and the dangers and refuse to accept that the crossing can never be made. If a single traveler cannot survive it, Perhaps a journey could be built that does not depend on a single life at all. Perhaps the answer is not to cross the galaxy faster, but to cross it slower, and to carry the crossing forward not in one body, but in many, generation after generation, a journey longer than any civilization has ever lasted. And whether such a thing could ever truly be done, whether any living society could survive a voyage longer than all of recorded history, is the deepest and most human question of the entire night. That is where we go next. If a single human life is too short to cross the galaxy at ordinary speeds, and the price of bending time is to arrive alone in a forgotten future, then perhaps the journey was never meant for one person at all. Perhaps the only way to truly cross the Milky Way, slowly and safely, without the violence of near-light speed, is to build a world that carries the crossing forward through many lifetimes. To launch not a ship, but a small civilization, a sealed and self-contained vessel large enough to hold a living community, and to accept that the people who finally arrive will not be the people who departed. They will be the distant descendants, born in transit, of a crew long dead. This is the idea of the generation ship, and it is at once the most hopeful and the most sorrowful answer of the entire night. Think for a moment about what life aboard such a ship would actually be. The first crew would board it as volunteers, knowing they had chosen the voyage with open eyes, but their children would not have chosen it, nor would their children's children, nor the 100 generations that followed after them. Whole human lives would begin and end inside those metal walls. People who were born in transit, who lived their entire span in transit, and who died in transit, never once setting foot upon a planet, never seeing a true horizon, never knowing a sky that was not painted on the inside of a hull. They would inherit a mission set in motion by ancestors as distant and strange to them as the builders of the first cities are to us, and they would be asked to carry it faithfully onward, toward a destination that they themselves would never live to reach. There is a darker possibility still, one that quietly haunts everyone who thinks seriously about these ships. Across such enormous spans of time, the travelers might simply forget. Knowledge fades, stories drift and change in the retelling. Purposes are lost. It is entirely possible that after enough generations, the people aboard would no longer remember that they were on a ship at all. The vessel would become their whole universe, its walls the edge of the world, its long-ago mission a half-remembered myth, if it was remembered at all. They would live and die believing the ship was everything there was, never knowing they were in the middle of a crossing begun by people long since turned to dust. To send a generation ship across the galaxy, then, is not only to ask whether a machine can endure, it is to ask whether a memory, a purpose, a fragile thread of human meaning can survive a journey longer than the whole of recorded history. And little in our experience gives us reason to believe that it can. The logic of it is simple. If you cannot make the journey short, then you make the journey livable, and you let the long years pass while ordinary human lives unfold within the ship. Children would be born aboard. They would grow up knowing nothing but the corridors and chambers of the vessel, never having seen the world their ancestors left. They would grow old and die, and their children would take their place, and so on, generation after generation, the ship a tiny moving homeland drifting through the immense dark, its passengers living and loving and dying along the way, the destination always still ahead, beyond the lives of everyone aboard. But here the timescales return to crush us once more. Without the magic of time dilation, a crossing of the galaxy takes the full span we calculated earlier. Even at a substantial fraction of light speed, the home frame journey across 100,000 light-years stretches across an unfathomable number of human generations. We are not speaking of a voyage of decades or centuries, but of a span far longer than the entire history of human civilization. Longer than the time since the first city was built, longer than the time since the first written word. A generation ship crossing the galaxy at any speed we could actually achieve would have to sustain a living, functioning society across more generations than have existed in all of recorded human history, and then many times more on top of that. And this is where the true difficulty lies. And it is not a difficulty of engines or fuel. It is a difficulty of endurance. No human society has ever lasted that long. No nation, no empire, no language, no faith, no institution of any kind has endured even 10,000 years in unbroken continuity. And a galactic crossing would demand stability across spans that dwarf 10,000 years many times over. Could a community survive that long sealed inside a single vessel, with no new land, no escape, no outside world to absorb its conflicts? Could it pass down the knowledge of how to maintain the ship, generation after generation, without ever forgetting, without ever falling into ruin or war or simple decay? Could the descendants centuries into the voyage even remember why they were travelling, or believe in a destination none of them would ever see? There is a haunting possibility, often imagined, that the people aboard such a ship might eventually forget they are aboard a ship at all, coming to believe that the vessel is the entire universe, the stars beyond merely lights painted on a ceiling, the original mission lost to time and myth. There is another path, some imagine, a way to skip across the long years without living through them. The idea of suspended animation, of slowing the body to a near stop, freezing or chilling the crew into a deep sleep from which they might wake, unchanged, at journey's end. If the travellers did not age during the crossing, if they could simply sleep through the millennia, then perhaps the impossible endurance would not be needed. But this too remains far beyond us. We do not know how to halt a human life and restart it. The freezing that would preserve the body also tends to destroy it, ice forming within the cells and tearing them apart. And even a sleeping crew would need a ship that could fly itself, repair itself, and protect itself across spans longer than our entire species has existed, with no waking hand to guide it. The honest answer, when we ask whether any of this could truly be done, is that nobody knows. We can imagine it, we cannot yet build it. And the gap between imagining and building, across these distances, may be the widest gap of all. There is a strange and unsettling twist buried in all of this, one that turns the question inside out. We have spent the night discovering how nearly impossible it is for us to cross the galaxy. And yet, when you step back and look at the numbers from a great distance, a different conclusion emerges, one that has troubled thoughtful people for decades. Even a slow crawl of generation ships, spreading patiently from star to star, settling one world and then launching outward again toward the next, could in principle carry a civilization across the entire galaxy in only a few million years. A few million years sounds enormous, and to a human life it is. But the galaxy itself is over 13 billion years old. A few million years against 13 billion years is the blink of an eye, a single afternoon against a long lifetime. Which means that if even one civilization had ever arisen long ago and chosen to spread, slowly and patiently, across the stars, it could have crossed and settled the entire galaxy many times over by now, long before we ever appeared. So the galaxy could have been crossed. It could have been crossed and crossed again, filled edge to edge with the children of some ancient civilization that began its slow expansion, billions of years before the Earth had even cooled. The crossing that seems so impossible to us, when measured against the great age of the galaxy, becomes not only possible, but almost easy, a thing that should have happened many times in the long history of this spiral. And this is precisely what makes the silence so loud. Because when we look out across the galaxy, across all those hundreds of billions of stars, we see no sign of anyone, no ships, no signals, no settled worlds, no trace of any civilization that ever made the crossing. The galaxy that could so easily have been filled appears, as far as we can tell, to be empty. And no one knows why. It is one of the deepest and most disturbing questions we have, and tonight it sits quietly beneath everything we have explored. The crossing is possible across deep time. So where is everyone? Before we reach for answers, it helps to see how seriously this question has been taken, and how the silence itself was made precise. In the year 1961, a young American astronomer named Frank Drake gathered a small group of scientists at a radio observatory in Green Bank, West Virginia, to think carefully about how many communicating civilizations might exist in our galaxy right now. To organize the conversation, he wrote down a simple chain of multiplications, an equation that has carried his name ever since. It does not give a hard answer. It cannot. It simply breaks the great question into smaller ones, each a piece we might one day hope to measure. How many stars are born in the galaxy? How many of them have planets? How many of those planets could support life? How often life actually arises? How often that life grows intelligent? How often intelligence builds a civilization that sends signals out into space? And, most hauntingly of all, how long such a civilization survives before it falls silent. Multiply these together, and you arrive at a guess for how many voices ought to be calling out across the Milky Way at this very moment. Depending on how hopeful you are about each step, the answer can come out as a great and crowded number, a galaxy that should be alive with signals. And that is exactly what makes the quiet so strange. By many reasonable estimates, the sky should be full of voices. We have been listening for decades. We have heard nothing but the faint hiss of the stars. There are many proposed answers to that silence, and the honest truth is that we do not know which of them, if any, is correct. Perhaps the journey is simply far harder than our arithmetic suggests, and the long generations and the lethal radiation and the impossible weight of fuel prove too much for anyone, anywhere, ever to overcome. Perhaps civilizations do arise, but rarely, and burn themselves out or destroy themselves before they ever learn to leave their home worlds, the way a candle gutters and dies before the room is ever lit. Perhaps there is some great filter lying somewhere along the path from lifeless rock to star-faring civilization, a barrier so difficult that almost nothing makes it through, and we ourselves may not yet have passed it. Or perhaps, strangest of all, we are simply early, among the very first minds to open our eyes in a galaxy that has only lately grown calm and rich enough to allow us, with the great age of crossings and settled worlds still ahead, in a future we ourselves will never see. Each of these is only a guess. None has been proven. The silence remains, vast and patient, and we sit beneath it without an answer. And yet, even now, in the smallest and most fragile way imaginable, we have already begun our own attempt at the crossing. In the year 1977, 2 probes called Voyager were launched, and bolted to the side of each one was a golden phonograph record, a message sealed against the ages. Onto those records were etched the sounds and images of our world. Greetings spoken in dozens of human languages, the cry of a newborn child, music from many cultures, the songs of whales in the deep ocean, a map showing where, among all the stars, our small world may be found. The 2 probes have now passed beyond the edge of the sun's influence and drift in the true space between the stars, the first things ever made by human hands to do so. They move far too slowly to ever truly cross the galaxy, and tens of thousands of years will pass before either one so much as approaches another star. But they are out there tonight, in the dark, carrying their small golden message of who we were, sailing outward on a voyage that will outlast every one of us, and very likely outlast the whole human race that made them. If we truly did cross, there is one place we could not avoid, one region every grand journey across the galaxy must reckon with. To pass through the heart of the Milky Way is to approach a thing of almost unimaginable power. At the very center of our galaxy, around which the sun and all the stars endlessly wheel, sits a supermassive black hole, a region of gravity so extreme that not even light can escape it, with a mass equal to roughly 4 million times the mass of our sun, all of it compressed into a point from which nothing returns. We call it Sagittarius A star. For a long time it was only a suspicion, a strange radio glow at the galactic center. But over the course of decades, astronomers proved its existence in one of the most patient and beautiful observations ever made. 2 teams, one led by an American astronomer named 'Andrea' 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 'And spent years watching the stars closest to the galactic center, tracking their motions night after night, year after year. And they watched those stars do something astonishing. They watched them whip around an invisible point at tremendous speed, one particular star swinging around it in a tight, fast orbit, accelerating to enormous velocities as it rounded the unseen mass and then slinging away again. There was only one thing that could anchor such orbits, only one thing massive enough and small enough to hold those stars in their frantic dance. An enormous black hole. For this work, mapping the dark heart of our galaxy by the motion of the stars that circle it, the two scientists shared a Nobel Prize in the year 2020. And just 2 years later, in the year 2022, a worldwide network of telescopes working together captured an actual image of the glowing ring of matter swirling around Sagittarius A star, our first true picture of the monster at the center of our home. To cross the galaxy through its center, then, would mean braving a region crowded with stars packed far more densely than in our quiet outskirts, flooded with radiation, swept by violent forces, all of it orbiting that vast and patient darkness. The heart of the Milky Way is no place for a fragile traveler, and so even the route of the crossing carries its own peril. The bright crowded core, a gauntlet of light and gravity and radiation around a hole in space from which nothing escapes. Put all of it together, and the shape of the true crossing comes clear. It would outlast nations and languages and faiths. It would require a society to endure longer than all of human history combined, or a sleep we do not know how to grant, or a speed that turns the void to fire and the years to a slow heartbreak. It would mean threading through a turning galaxy, past an invisible ocean of dark matter, perhaps through the radiation-soaked heart where a 4 million sun darkness waits, and the travelers, however they made it, would arrive as strangers in a galaxy that had wheeled onward beneath them, in a future so distant that everything of their origin had long since turned to dust and silence. The crossing is not impossible. We have seen that clearly tonight, but it is a thing so vast in time and so costly in everything that makes us human that to truly contemplate it is to feel the full weight of our smallness and the full strangeness of the universe we have been born into. And it is in that smallness, that strange and quiet smallness, that the last and gentlest part of our journey begins. So where does all of this leave us, lying here in the quiet dark, having travelled in our minds from one edge of the galaxy to the other, and found the crossing almost beyond imagining? We came tonight with a simple question, the kind a child might ask while staring up at the band of light in a summer sky. How long would it really take to cross the Milky Way? And we have followed that question down through layer after layer, past the speed of light and the limits of our machines, past the strange bending of time and the hidden dangers of the void, all the way to the silent, turning heart of our galaxy. The question was simple. The answer, we have found, is anything but. Perhaps the crossing is something we are meant to attempt, no matter the cost. Perhaps it is written into us, this reaching outward, this quiet refusal to accept the edge of the map as the edge of the possible. Perhaps a people who stop reaching have already begun, in some small way, to die, and the long and patient effort to cross the impossible distance, even across 100,000 years and 1,000 generations, would be the most human thing we ever did. Perhaps it would justify every hardship that came before it, every loss, every long night of doubt, a single thread of light drawn across the dark between the stars. Or perhaps the opposite is the deeper truth. Perhaps the human spirit needs a home far more than it needs a frontier. Perhaps the dream of crossing the galaxy asks us to surrender too much, to scatter ourselves into the cold, to send our children out into a darkness from which they can never return, all for a distant shore that none of us now living will ever set foot upon. Perhaps the wisdom lies not in the leaving but in the staying, in tending the small warm world we already have, in loving the people who are close enough to touch. These are not questions that science can settle for us. The equations can tell us how long the journey takes and how much it would cost. They can map the dangers and weigh the fuel, but they fall silent before the only question that finally matters, which is whether the crossing would be worth it. And that is a question of the heart, not of physics. Different people will answer it differently, and none of them will be wrong. Some will look at the long dark distance and feel a longing so strong it aches, a need to go, to see, to know what lies on the far side of our home. Others will look at the same distance and feel only the pull of the world behind them, the warmth of an ordinary life, the quiet sufficiency of a single human span. Both of these are true. Both of these are human. The universe does not insist that we choose, and tonight, lying here in the dark, neither will we. But whatever you might decide, there is something worth carrying with you out of this long journey, something that has been quietly waiting beneath every number we have spoken tonight. It is this: the distance was never truly the wall. We learned that hours ago, though it may not have felt like a lesson at the time. The galaxy is impossibly wide, yes, 100,000 years across at the speed of light itself. But space, in the end, was never the thing that truly stopped us. Time was. The wall between us and the far rim of the Milky Way was never really made of miles. It was made of years, of human lifetimes too short to span the gulf, of civilizations too fragile to endure the weight. And the one door we found through that wall, the strange and beautiful loophole of time itself slowing as we approach the speed of light, opens only in one direction. It opens forward. A traveler could cross the galaxy in the span of a single life, but only by leaving their own time behind forever, arriving in a future so distant that everything they had ever known would long since have crumbled into dust. The door opens forward. It never opens back. And whether you would step through such a door knowing the price is perhaps the most personal question this whole vast subject finally asks of you. It all depends, in the end, on whose clock you are reading. That was the quiet truth hidden inside our question from the very first minute. There is no single answer to how long it takes to cross the Milky Way, because time itself is not single. To the patient light, 100,000 years. To the home you left behind, the same. But to the traveler aboard a ship riding the edge of the possible, perhaps only a handful of years, a few short turns of a private clock, while 100 millennia poured past outside. The crossing is not one length. It is many lengths at once, each one true for whoever is living it. And there is something in that idea, strange as it is, that feels almost like comfort. The universe does not hold a single master clock above us all, ticking down. It holds 1,000 million clocks, and yours is the one beating softly in your chest right now, in the dark, as you listen. So let us step back, one final time, and feel the true size of the stage that all of this has played out upon. You are lying on a small wet rock, circling an ordinary star, one of hundreds of billions of stars, far out toward the rim of a single spiral galaxy. And that galaxy is itself only one of hundreds of billions of galaxies, scattered through a cosmos that stretches, as best we are able to measure it, some 93 billion light-years from one side of the observable universe to the other. The Milky Way that we have spent this whole long night struggling to cross, this wheel so vast that light needs 1,000 centuries to span it, is itself no more than a single faint mote of light in that greater ocean. If crossing our own galaxy lies so far beyond our reach, then crossing the universe is a thing the human mind can barely even frame. And you, the one listening, the one breathing slowly in the quiet, are smaller against all of that than a single grain of sand against all the deserts and all the beaches of the earth combined. And yet, here is the thing that should settle over you now, gently, as the weight of all that vastness presses down. That smallness is not the end of the story. It is not a cause for despair, and it never was. Because you, that single grain of sand, lying in the dark on a small blue world, have just done something that the entire silent turning galaxy cannot do. You have understood it. You have held the whole impossible width of the Milky Way inside your mind. You have weighed the speed of light and the bending of time, and the long patience of the stars, and you have felt, however faintly, the true shape of the cosmos you were born into. The galaxy does not know how vast it is. The stars do not know how far apart they lie. Only minds like yours, fragile and brief and impossibly rare, have ever looked out across all that emptiness and grasped what it means. In a universe 93 billion light-years wide and almost entirely empty and cold, you are one of the rarest things there is. You are a part of the cosmos that has woken up and looked around and wondered. We may never cross the Milky Way. The honest answer, the one we promised at the beginning, is that no one truly knows whether it will ever be done, or whether anyone, anywhere, has ever done it. The distances are crushing. The time is longer than nations, longer than languages, longer than memory itself. The price is everything that makes a journey worth taking. And still, knowing all of that, something in us leans forward into the dark, the way it always has. The way it did when the first of our kind looked up from the plains and wondered what those lights were. We are very small, and the night is very long, and the far shore may forever lie beyond us. But the reaching itself, the wondering itself, is not nothing. It may, in the end, be the most precious thing we have. So rest now. Let the vastness hold you, not as a threat, but as a kind of dark and gentle blanket drawn across the whole turning sky. The galaxy will keep its slow turning whether or not we ever cross it, and there is a peace in that. A permission to simply be small and warm and here. We may never